The bivariate analysis implies the use of at least two variables.
To start the bivariate analysis, we are going to see if there is any trend on the data. To do that one, we are going to use the script number 31. This script is about the polynomial regression fitting, and this script was created at the lesson 4th of the second geostatistic course. Script 31, polynomial regression fitting. Then the layer is going to be the data set. For the x-axis, we are going to add the x coordinates. For the y-axis, we are going to add the groundwater without any type of transformation. X and y, you have to know that in this case, what we are doing is a scatter plot. Then x is going to be the x coordinate, y is going to be the groundwater elevation, and title of the graph is going to be trend analysis. And for the subtitle, we can put raw data. I'm going to pass the video faster. Then we can run this script. Double click to open. And let's go to make this screen bigger. In this graph, we can see how the three different types of polynomial are fitting on the data. We have first order polynomial, second order polynomial, and third order polynomial, each of them with different colors. And what we can see is that the data, that is the black dots, are showing a trend in this direction. Then we can say that the first order polynomial and also the second order polynomial, they are fitting well on the data. But for the third order polynomial, we can see that there is no too much differences between the second and the third order. Then we can consider that the third order could be an overfit on the data. Now we can do the same graph, but instead to use the x coordinate, we are going to use the y coordinate to see if there is any trend in that direction. Then we can go here, change the x for the y, and now we can run this script again. Double click to open, and let's go to make this screen bigger. In this case, also we can see a trend in this direction, but between the three of them, it's not clear the second order and the third order. It's pretty clear for a first order, but there is not too much differences between the first order with the second and third order. Then the third order is going to be overfit, and the second order it's not really clear, right? But we can go further with the analysis of first and second order later with a different scripts and also different type of analysis. That is going to be not graphical, is going to be quantitative analysis. Now let's go to talk a little bit about the universal Kriging and what is the most interesting thing about this method. I created the next slide. And here we can say that the universal Kriging assumes this model. And what we have here? Z is the variable of interest, is the main variable. In this case, is the groundwater elevation. And this groundwater elevation is located at the space in these coordinates. S sub y is the coordinates at the space. It could be x, it could be x and y, it could be x and y and z. You know, it's a location at the space. And this variable is equal to two different terms. The first term is the deterministic one. And as you can see, it has also a spatial location. And the second term is the stochastic part of the model. This term is known as an error, but most commonly it's known as a residual. And this residual value has also coordinates at the space, has a location at the space. And this location is the same as this one and is the same as this one. For one specific point or for one specific sample or for one specific measurement at the space, okay? The deterministic part of the model is the trend. In this case, as we are working in 2 dimensions, because we have just the groundwater elevation and the x coordinate, it is a line. For example, if we take the first order, it's going to be the red line. But if we are working in 3 dimensions, it's going to be a plane. That is going to be the real case for this scenario, because we are working in 3 dimensions. We have x, y, and we have the z that is going to be the groundwater elevation. Then the interesting part for the deterministic model is that we know everything. We know all the information related to this value, because that is deterministic. You know, we have all the data. For all the points on the line, we can have all the values for this part of the model. We have a function that can provide all these values. And these values are going to be the same always. It's going to be the same for yesterday, it's going to be the same for today, and it's going to be the same for tomorrow. That's the deterministic part of the model. The things that are changing is the stochastic part of the model. And let me put you an example. I remember a friend of mine that told me one time that if you take 2 consecutive measurements of the groundwater elevation in a well, for example, you are going to have always different values. We are talking here about millimetric precision, right? Because if you are taking centimetric or decimetric precision, you can have the same values. But as you are adding more decimals, the differences between these 2 consecutive measurements are going to be more significant. Other example could be if you are taking 2 samples of soil to measure the concentration of sodium. If you are taking 2 samples at the same location at the same moment, and you send that samples to the lab, you are going to see that the concentration for the sodium for these 2 samples are going to be different. Then that is the stochastic part of the model, right? It's the part that we can consider that is pretty random, because it's changing. You know, you are never going to get the same result. However, the deterministic part of the model never changes. It's always the same. And also we are going to have the values in a continuous way. We have all the values for all the locations at the space, because we have the information in a continuous way. In a 2 dimensions, it's going to be a line, all the information, all the points in this line. But for a 3 dimensions, all the points located on the plane. But as you can see, the stochastic part, that is the part associated with the probability, we don't have information in a continuous way. We have the information that is associated with the locations where we took the samples. And even this information is pretty random, as I said, because can change. Then in order to solve this equation, we need to know these 2 terms. The deterministic part of the model, that is the linear regression model, to know what is the trend, and the stochastic part. This stochastic part is the ordinary Kriging. Then when we plus these 2 things, we can solve the universal Kriging. But the limitations of the universal Kriging are related to the analysis of the regression, the analysis of the trend. Because here, when we are using universal Kriging, we can use only the linear regressions. But when we are working with regression Kriging, we can use different models, different type of regressions here to have a more realistic trend on the data. You know, in order to determine what is the deterministic part of the model and what is the stochastic part of the model, the limit, it's so complicated. I'm going to say it's almost impossible, you know. What is going to be the real deterministic part of the model? No one's know that information, right? Then if we have more models, more regression models that we can use to establish the trend on the data, we can have better results. Because as I said, it's very complicated, to find the limit between the deterministic and the stochastic. It is more flexible. The regression Kriging is more flexible to solve this model. But the regression Kriging, we have to work separately with the regression model and with the stochastic part. But with universal Kriging, we can do both things together. We don't have to work separately. And that's the advantage of universal Kriging. We can do everything just using one script. As you are going to see later, universal Kriging is doing everything for us. It's going to remove the trend from the data, it's going to provide the residual values, and at the end, what we are going to get is the prediction of those locations where we don't have any sample. But when we are working with regression Kriging, what we have to do is first calculate the deterministic model, then calculate the stochastic model, and then we have to plus both of them manually. I can imagine that at this point everything looks pretty abstract and even very complicated, but you are going to see in this lesson that is about universal Kriging, and also in the next lesson that is going to be about regression Kriging, that everything is going to make sense, right? But at the beginning, the theoretical part sometimes is complicated to understand, but when we are doing the practical part of this lesson, you are going to see that the things make sense. And also then with the next lesson about regression Kriging, you are going to have a full understanding of all these concepts. Also, my recommendation is to watch the fourth lesson of the second geostatistics course, where we was talking about the less squares. Remember, as I said, the universal Kriging can use the ordinary less squares and also the generalized less squares. And the ordinary less squares, it was explained in that lesson. And I'm not going to go to explain anything here, just take a review of that lesson. Also in that lesson, we was talking about simple regression for the second order trend surface and also for the first order trend surface. And we was talking about the residuals, the fitting values, and all this information. It's really important to have a full understanding of these concepts. As this exercise based on the World Camp Aquifer dataset is based on 3 dimensions, we are going to pass directly to the multiple regression analysis, and we are not going to do anything related with the simple regression analysis. Then the next step is to do a 3D interpretation of our data, where we are going to see the plane associated with the trend on the data. Also be aware that this trend, this plane, is fit on the data according to the ordinary less squares, okay? And to do that one, we are going to use the script number 49. Is this script over here? And it comes from the 5th lesson of the second geostatistics course. Then here we are going to add the X coordinate, here the Y coordinate, and here the groundwater elevation. Remember that we are going to fit a surface of first order according to the ordinary less squares on the Wolfram Aquifer dataset. Then here we have a couple of angles to play, the horizontal angle and also the vertical angle. At the beginning we can put here 30 degrees. And the title of the graph is going to be Trend Analysis. Trend Analysis for the first order. Label X is going to be the X coordinate. Label Y is going to be the Y coordinate. And label Z is going to be the groundwater elevation. I make a mistake here, elevation. And then we can run this script. Double click to open. And let's go to make this screen bigger. And as you can see, this is the first order plane or surface, okay? And here we have the residual values. Is these dots over here? Sometimes we have the residual values over the plane, and sometimes we have the residual values under the plane. Here is the legend for the groundwater elevation according to the colors, and here we have the X coordinate and the Y coordinate, and here the groundwater elevation. Now we can change the values associated with the angles to see better the plane. Then we can go here and put here 215, and here, for example, 30 degrees. And we can run this one again. And double click to open. Here we have a different angle to see the plane. You can see again the residual values over the plane and also under the plane. Let me make this one bigger also. Now we are going to do the same, but instead to fit a first order surface, what we are going to fit is a second order surface. This is just a visual representation of the data. Then we are going to see what is the regression that fits better on the data, and we are going to justify what type of trend we are going to decide to use for the universal Kriging. Then we can move here again, and in this case it's going to be the script number 50. As you can see here is saying trend surface second order. Then it's going to be the same X, Y, Z. We can put at the beginning also 30 degrees. Here is going to be trend analysis, second order. Then here for the label X is going to be X coordinate. For Y is going to be Y coordinate. All the coordinates and also the groundwater elevation is in meters. And then we can run this one. Double click to open, and let's go to make this one bigger. Then this one is for the second order, and remember that this one was for the first order. Here we have a flat plane, and here we have a curved plane. And now we are going to do the same, but for a different angle, and we are going to add the same. Here is going to be 215, and here is going to be 30 degrees. Then run. And double click to open. Let's go to make this one bigger. And then we can compare this one with this one, right? Flat and curve. First order, second order. And remember that both of these linear models has been fit using the ordinary least squares, okay? Because that's the one that we are going to use with universal Kriging. We can use also a different type of regression that is a generalized least square, but we are not going to see that one in this lesson. Maybe we can use that one in the regression Kriging. But just to let you know that here for the universal Kriging, we can use the ordinary least square and also the generalized least square to fit the linear model or the linear surface on the data associated with the trend, okay? We already make a visual representation of the trend surface on the data for the first order and for the second order. But now it's time to quantify numerically how good are these models, how good these models fit on the data, and how significant are the covariables, the x and y, for this model. And to do that one, we are going to use different scripts. Then first, we are going to use the number 40. And this script is known as a multiple regression residuals summary first order. Then that one is pretty easy. Just add the x coordinate, add the y coordinate, and add the z coordinate. That is going to be the groundwater. Then run the script. And here is telling us what formula we are using. That's the regression Kriging for the ordinary least squares, where we have the dependent variable, that is the groundwater elevation, and the independent variables, that is the x and the y. Also here we have some statistics for the residuals. We have the minimum value, we have the first quantile, we have the median, the third quantile, and the maximum value. These values again are associated with the residuals. And then we have the coefficients. The important thing here is that this value is smaller than 0.05 and this value is smaller than 0.05. Then what it is saying that the x coordinate and the y coordinate, as you can see here, x and y, they are very significant in the model. Okay, they make a very big influence in the model. Then here for this value that is the r squared, what is saying is that almost 90% of the variability associated with the groundwater elevation can be explained with these two variables, x and y, and that's really good. And also at the end, as we have a p-value that is less than 0.05, we can say that the model is significant, is good, is a good model, okay? But in order to use this model for the trend on the data, we have to do analysis of the residual values, okay? We know the model is good, but we are not sure yet if we can use this model for our data, because it is going to depend on the statistics of the residuals that we are going to see later. Now let's go to see the model associated with the second order trend surface. Then it's going to be the script number 41. Then we are going to do the same, x for the x coordinate, y for the y coordinate, and z for the groundwater. First, we want to make sure that the models are working and they are good. Then the next step is going to be the analysis of the residuals, right? Then in this case, we have here several parameters, because now the model is a little bit more complex. Here we have the formula, and now we are using different variables. We are using x, we are using y, we are using x squared, y squared, and the cross of y and x. Okay, all these coefficients we have now. And let's see how significant are these coefficients, right? The x is pretty significant. The y in this model is not significant. Well, still significant because it's smaller than 0.05. The x squared is not significant. The y squared is significant, and the cross is also significant. Then in general, this model also are really good because most of the coefficients are significant. The only one is not significant is the x squared. It's indicating that the x squared is not adding anything on the model. We can remove from this formula here the x squared because it's not adding anything to the model. Then the r squared for this model is even bigger as before, but that one makes sense, right? Because now we are adjusting to the data better, right? Because now we have a second order trend surface and we can adapt better to the data set. and it makes sense, right? And then also the model is significative in general because the value is smaller than 0.5. You have to understand that as bigger is the grade of the polynomial, higher is going to be this value, because better is going to be the fit on the data, right? But at the end, the important thing is that we need to have a valid model, but also we need to have a valid residual values. And at the end, what we want to take is the simple model. We don't want to overfit the trend on the data. We want something simple that can be justified with the structure of the aquifer, right? The most realistic scenario for the structure of the aquifer is to think in a trend that is first order or second order, you know, something that is bigger than second order. It doesn't make too much sense for me, okay? Then we are going to work with the first order and the second order. The next step is to extract the residual values for each of these models. Then let's go to start first for the first order surface. And I believe this one, second order, multiple regression analysis. We can close this one and we can leave these two at the moment, and also we can close this one at the bottom. Then we are going to run the script number 33. With the script number 33, we can extract the predicted and the residual values for the model that is related with the first order trend surface, okay? Then X is going to be X, Y is going to be Y, and Z is going to be the groundwater. Then we are going to save that spreadsheet, save file, at the lesson number 2, and it's going to be, I'm going to put this one like first and save, and then we can run. And now we can go here. It's going to be lesson 2, and we save with number 1, this one. Okay, open copy, and here, as you can see, we have the predicted values and the residual values. Now let's go to fix a little bit this table. Then I'm going to select all these ones from here to the end, to here, then copy, and I'm going to paste here. I'm going to select 2 columns, spatial paste, and it's going to be transpose, and OK. And then I'm going to remove all this, delete rows, OK. And that one, the number 1 is the residuals, and the other one is the predicted. Then this one is going to be residuals, and this one predicted. And let's go to fix this one, and here is going to be the observe. That's the values that we measure at the field, right? Then, as we set for the model, the residuals plus the predicted values, these predicted values are the fitted values on the model, okay? Is that the deterministic values for the model. Then is going to be equal to the observed values. This one plus this one is the observed values. Then we can run this one to the bottom. Then I'm going to remove these 2. Okay, and also I want to add here an ID, and this ID, we are going to use the ID to put together these 2 tables, right? Here we have an ID, and I want to put the same label as this one to join the tables with the attribute table, okay, of the data set related with the Volcam aquifer. Then here I'm going to add ID, and these values are going to be from 1 to 85. To 85, that's good. And I added the observed value because the observed value is going to be like quality control to make sure that the table here fit perfectly, okay? We want to have here this value, and here we want to have the same value. You are going to see later how we can use this one as a quality control of the residuals and predicted values. Then we can close, then fill, save as, and we want to save this one with the CSV format, okay? And again, that one is going to be first order. We are going to save like that, first order, and save. And now we can open that one here with the QGIS. Then project is going to be this one, the layer is going to be the limited test. Then select that file that is in lesson number 2, and is going to be, we didn't save with the first order. Keep the current format, and it's this one, okay. Make sure you have selected this option. This one is okay. We don't need these ones because it doesn't have any geometry. Then we can select this option, and that's the table we want. And add and close. And now we have the table over here, open attribute tables, and we are going to join this table with the attribute table. We can remove this one. Okay. Then to do that one, we are going to select this one. We are going to go to properties. Then we are going to go to join. Then add a join, and it's going to be this table. And the field we want to join is the ID. And the target field is going to be the ID again. We are using the ID for this table to join the ID for the attribute table. Okay? And apply. And okay. And now we can open the attribute table here. And as you can see, we have now the residual values added. And the quality control, as I said before, is that this value over here has to match with this value over here. If these values doesn't match, then we have a problem. Then you can check some of them. For example, number 10, this one and this one, you can see is the same value. For example, this one and this one, again is the same value. This one and this one, the same, and also this one. This one and this one are the same. That's indicating that the values is good, okay? Then we have now the residual value and also the predicted value, that is the fitted value on the model, and we have the UTM coordinates for each of these values over here. Now we are going to fix a little bit this table and make sure that we save this data at the attribute table. Then we are going to press the pencil to edit the table. Then we are going to go to this option over here, open field calculator, and we are going to create a new field. This new field is going to be first residual for the first order. I'm going to put like that. Then what I want here is a decimal real number, and I want 3 decimals. As you can see here, we have too much decimals. With 3 decimals is good. Then in this case is going to be, I'm going to put 1 multiply by this field over here. Then field and values is going to be the residual. Double click and okay. Okay, as this one is not working, as you can see, what I'm going to do is restart the QGIS. Okay, then I'm going to close this one, close all this stuff, I'm going to finish the edition here, discard, I don't want to save, then close, discard, and I'm going to start the software again. Sometimes it happens. Sorry, I did the wrong one. It's this one, and I can close this one. And now double click again. I have the data. I'm going to add the table. Then it's going to be this format. Select this one, open, everything is good, add, close, select this one, go to properties, then add this one, ID and ID, okay, apply and okay, then open the attribute table, select the pencil to edit, open the field calculator, then here is going to be residual, first order, then it's going to be decimal number, 10 and 3 is good, and this one is going to be 1 multiplied by the value that is this one, then okay. And now you can see we have the value over here. Then make sure that you save this one, and let's go to do the same for the predicted values, that is the fitted values. Then field calculator, I'm going to put here fitted values, I like more, fit like this, fit first order, and this one is decimal, 3 decimals is good, and it's going to be 1 multiplied by the column that is the predicted. Double click, you can see the value over here, okay, and then we have both. Then we can say that this part, the residuals, are the stochastic part of the model, and the fit is the deterministic part of the model, right? And the groundwater elevation is this one, and this one also is the main variable. Now what we can do is remove these 3 columns because we don't longer need these ones. Then just press this option here, delay fields, and we are going to delay this one, and this one. Even we don't need to delete these ones. If you save this one, save, and then when you close this one and you remove this table over here, remove the layer, okay, then when you open again the attribute table, you are going to see that columns are no longer exist, okay. Now I am going to do the same, but for the second order trend surface. Then let's go to R, let's go to the course, this option over here, and it's 44, I believe. Let me check this one. Okay, that's multiple regression residuals and predicted values for the second order. Is this script, then X, Y, and Z, that is going to be the groundwater, and I'm going to save here with this one, but that one is going to be second. Then save and run. Then we can go to the folder here, not this one, number 2 is this one. Double click to open, and let's go here, okay, and open copy. And we are going to do now exactly the same as we did for the first order, but I'm going to close the video here, and I'm going to show you the results because the video is taking very long, and you know already how to do all this stuff and what it means, because it's the same as the first order but for the second order. I already created the table for the second order trend surface, and now I'm going to open this table with QGIS. Now I am going to add the table to the data set, to the attribute table at the data set. Then join, add, is going to be this table, ID and ID, okay, apply and okay. And now if I open the attribute table here, we have for the second order trend surface the values. Then again, we want to see if these values in this column match with these values in this column. And as you can see, all the values are matching. Then it passed the quality control for the groundwater elevation, indicating that the location of the residuals and the fitted values are good. And here we have the coordinates. Now I'm going to fix this table to have the columns as this one, because we don't want too many decimals and we don't want these names that are very long. Okay, I already added the new columns. Then I'm going to save, and I'm going to close this one, and I'm going to remove this layer over here. Okay, and now I have already the final attribute table, where we have the first order and the second order trend surface. Now we have the data on the attribute table, and we are ready to analyze if the residuals cover the expectations that we need to validate the model, and then to use that trend for the data for the universal Kriging. As we already know, the universal Kriging assumes a model that is formed with two different parts. The first part is the deterministic, and it is the fitted values, it is the trend. And the second part is the stochastic, it is the residual values, it is the error. And if we want to have a valid regression model, the residual part, the stochastic part of the model, has to cover some assumptions. If we take, for example, the first order trend surface, we have these two columns. Then the first column is the residuals, and this one is the stochastic part. And the second column is the fitted values, and this one is the deterministic part. Then for the residual, for the errors, we have to cover some assumptions. And the first assumption is going to be that the values has to be normally distributed. Then we have to check this assumption in order to verify that this regression model is valid. And that's what we are going to do now. Then we are going to use the script number 13. It's going to be over here. 13, double click to open. The parameter is going to be the residuals for the first order trend surface. Later we can do for the second order trend surface. The values for X is going to be residuals for the groundwater elevation in meters. The label Y is going to be number of samples. Title of the graph is going to be histogram. Subtitle is going to be residuals, raw data. And then we are going to take the range from the attribute table. I'm going to pass the video faster. I already add all the labels. Now I'm going to add the minimum value, then go to the attribute tables, the residual, and let's go to pick up the minimum value. The minimum value is this one, then copy, and let's go to paste over here. Paste. Now let's go to take the maximum value. I'm going to close this one. Residuals, maximum value is this one. Copy and paste over here. Paste. Now we want to have the difference, but we want the absolute value. Then we are going to take this one as a positive, okay? Because we want to know what is all the range, all the distance from the minimum to the maximum. Then let's go to pick up the calculator and plus these two numbers. Then it's going to be 112.329 plus 199.444. This one is equal to this value divided by 10 because it's the number of bins I want. And this one is going to be the interval. Then copy this value and paste over here. Control C, Control V. I didn't copy the value. copy. Something is wrong here. Let me see now. Now it's working, and now we can run the script. And double click to open. Let's go to make this screen bigger. Now we can analyze the histogram and the box plot together. The first thing is that we have one outlier over here, and that is not a good thing. The second thing is that the box plot is not situated at the middle of the graph. It's situated a little bit to the left. And we wish to have the box plot at the middle of the graph. The third thing is that the mean and median value, they are not together. They are a little bit separated. That's also not good. And the last thing is that the data looks pretty normally distributed, and that's a good thing. Now we can run the Kolmogorov-Smirnov test to quantify numerically the normality of the data. Then it's going to be the script number 18. Then we want to run with the residuals of the first order. Then run. And as the value is bigger than 0.05, we can say that the data is normally distributed. Now, the second assumption that we have to cover for the residuals is that the residual values and the fitted values doesn't have any relation. Then to do that one, we are going to use the script number 19. Is this script over here, and then we are going to do a scatter plot between the residual against the fitted values. Remember that if you want to implement this script, just watch the first lesson of the second geostatistics course. Then to do that one, for the X is going to be the fitted values for the first order trend surface. The Y is going to be the residual values for the first order trend surface. Then X is going to be fitted values, Y is going to be residual values. The title is going to be a scatter plot, and for the subtitle is going to be residuals versus fitted values. I'm going to pass the video faster. I already brought everything. Now we can run the script. Double click to open, and let's go to make this screen bigger. We say that for the second assumption, we cannot have any relation between the residual values and the fitted values. But what does it mean? It means that we cannot have any trend, any pattern between the residuals and the fitted values. What we want is to have the data distributed randomly. Remember that when we remove the trend from the data, this one is the trend and the red dots are the data. When we remove this line, that is the regression line, from the data, we made this trend to be 0, as you can see in this graph, right? Then here, when we remove the trend, what we have the trend here for the value 0, then we no longer have any trend on the data. We remove the trend. But if still a trend on the data, that is a problem. And then we are not going to cover the second assumption. And if we are not covering the second assumption, the regression model is no good, because we don't want to have any relation between the residuals and the fitted values. Because at the end, what we want is to use the residuals to do the ordinary Kriging. And as you remember, as we explained at the first lesson of the third geostatistics course, we was talking about the stationarity. And one very important assumption of the stationarity is to have the mean value constant. And we was talking about this slide over here. And what we have here is the data set, and this data set is showing a constant mean. As you can see, the mean is constant. And here we have another example where the mean is not constant because the mean is increasing. Then again, in this case, what we have to do is remove the trend, make this trend to be 0, and when we make this trend 0, what we are going to have is something like that, where the mean now is 0, but all this data set is going to be located here if 0 is over here, right? And that's what we have in our graph, right? The trend is over here and has a value of 0. And now our data is no longer showing any trend. But if the data of the residuals, again the fitted values, are still showing a trend, it means that we didn't fit properly the order of the polynomial. Maybe we have to fit one more degree on the polynomial in order to remove that trend from the data. Then if we have a trend in this graph, we have to try to change a different order of polynomial, right? And also if the trend persists, maybe we have to think in a transform the original data. It's, all the time is exploring the data and making change on the data in order to get the results that you want, right? Then if this graph is still showing a trend after fitting, for example, the first order polynomial, then you have to try with the second order polynomial, if there is any trend or not. If still the trend, maybe you want to do any transformation on the original data and try to fit again the second order polynomial or the first order polynomial and see if there is any trend. At the end, the goal is to remove any relation between the residual values and the fitted values. And now let's go to talk about the third assumption. In the third assumption, what we want is that the data presents homoscedasticity. It means that the data of the residuals has to present the variance constant. If the variance is not constant, again, the regression model is not going to be valid. It happens also the same for the stationarity of the data. Remember that when we was talking about the stationarity, we need the variance to be constant. And again, we can use the same example. In this case, the variance is constant. In this case, the variance is constant. In this case, the variance is not constant. Because as you can see, this distribution of the data, like in a fan distribution, the variance is increasing. Also here, because here the data has this white, but here has this white. It's indicating that the variance is increasing. What we want is to have the residual values here that are distributed equally in all the range of the fitted values. And it is not happening in this graph, right? Because here we have 100 and here we have 100. And for these values it's okay, but here we have one value that it can be considered as an outlier that make the distribution of the residual values in the range of the fitted values not equal, because we have this value over here that can make the variance be not constant. And if the variance is not constant, then our regression model is not valid. Then in this case, if the variance is not constant, what we can do is change the order of polynomial that we fit on the data. If it doesn't work, maybe we can do a data transformation and try to fit the polynomial again to see what happened. If that one doesn't work, we can decide, for example, in a state to use a universal Kriging, use a regression Kriging, and with regression Kriging, as you already know, we are more flexible to adjust different regression models on the data. There are different options, right? But what you need is to have a regression model that is valid, okay? That's the final point. Now let's go to see a different graph that also is going to help us to recognize if there is any relation between the residual values and the fitted values. But in this case, it's going to be a kind of 3D interpretation, okay, of the residual values. It is the script number 53, and this script was created at the second geostatistics course, lesson number 6. Is this one over here? Then we have to add the x for the x coordinate, y for the y coordinate, z is going to be the residuals for the first order, and it's just a scatter plot. Then for the label x is going to be the x coordinate. It is in meters. For the label y is going to be the y coordinates. Remember that in this case, I say previously that is kind of 3D dimensions because we are using the x and the y coordinate, and also as a z we are using the groundwater elevation for the residuals, right? Then it's going to be a 2D map but 3D interpretation, okay? And for the title of the graph is going to be Residuals First Order Trend Surface. And for the legend, Residuals. Then we can run this script. Double click to open, and let's go to make this screen bigger. As you can see, it's a bubble map. As bigger is the bubble, bigger is the residual value. We have the blue is the positive values and the red is the negative values. We can add that information at the legend. Then we can go here and put here, for example, at the legend, we can put legend, then blue equal to positive values and red equal to negative values. And then we can run this one again. Double click to open. Let's go to make this one bigger, and we can remove this one. Then in this graph, what we want to see if there is any trend again, okay? As you can see, the positive and negative values are distributed randomly, okay? Then it is indicating that there is no any trend. You can imagine, for example, if you have blue color here in this area and blue color here in this area and all at the middle, for example, in a red color, it is indicating a kind of a second order trend surface, right? But in this case, as positive and negative values are distributed pretty randomly, it is indicating that there is no trend. Also, another problem could be, for example, that here we have all blue colors and here in this area all red colors. Again, that one is going to be a trend of first order. Also, the bubble map is really good to recognize any outlier, and here, as this value is really big compared with the rest of the values, also we can consider that this value as it is an spatial outlier, okay? And it is interesting that this value is the same as this value and is the same as this value. And then we can say that this value, it's a distribution outlier because it's outlier here at the distribution. and it is also an spatial outlier because, as you can see, it's bigger, too much bigger compared with the rest of the residuals. Then, as a summary for the first order trend surface, what we can see is that the data is normally distributed, but there is room for an improvement. The relation between the residuals and the fitted values looks like there is no relation, there is no trend. Then we can assume a constant mean, but for the third assumption that is related with the constant variance, as we have this value over here, maybe we are not covering that assumption, right? And also we can say that this outlier, this one, is not only a distributional outlier, it's also an spatial outlier. Then the first order trend surface model, it's not good at this point. Now let's go to see what happened with the second order trend surface. Let's see if the model improve using the second order trend surface. Then we are going to do all these steps, but for the second order trend surface. Let's start with the histogram plus the box plot. Then go here. It's not this one. It's not this one. It's not this one. Then it's going to be this one. For this one, we have to change this one for the residuals for the second order. And now residuals, here I'm going to put second order also. Residual data, second order. And here I have to add the minimum and the maximum value, then go to the attribute table. Going to make this one smaller, then go here for the second order, this one, and this one is the smaller one. Copy, and I'm going to paste over here. Paste, and now I'm going to do the same. Going to close this one. For the maximum value, in this case is this one. Copy and paste over here. Paste. Now I'm going to do the difference, then calculator. But I want the range, the maximum distance, you know. Then I'm going to take this value as a positive. It's going to be 124.750 plus 201.443 equal divided by 10. Then I'm going to copy this value, copy, and I'm going to paste over here. Paste. Now I can run this one. Double click to open, and I'm going to make the screen bigger. And now we can compare this one with the first order. Make this screen bigger. And as you can see, this one is a little bit better. Why? Because the mean value and the median, they are a little bit more together. But we still having the problem related with the outlier, the distributional one over here. But if we compare both of them, you can see the improvement of the second order. Looks better, right? Now let's go to do the scatter plot. Then go here and let's go to select the scatter plot. That is going to be scatter plot, this one over here, and fitted is going to be fitted second order, and residuals the second order. And here is going to be second order, and we can run this one and double click to open. Let's go to make this one bigger, and we can compare with this one to see if something changed. And I'm going to say that not that much. We have more or less the same result. And again, we have the outlier over here, right? But also there is doesn't look like any relation between the residuals and the fitted values. And now we are going to do the last one. That is going to be, the post plot by the side for the residuals. Then again, this one is going to be for the second order. And then we can run this one. And double click to open. And let's go to make this screen bigger to compare with this one. Again, there is not too much differences between the first order trend surface and the second order trend surface. I didn't change the name here. Let me change the name, the title I mean, here to avoid any confusion. Then go here, and here is going to be second. Then run this one again. Double click to open. And let's go to make this one bigger. We have again the spatial outlier over here. And the distribution and positive and negative numbers looks pretty random, indicating no relation between the fitted and the residuals. But also with the first order, we have the same, right? Then, as a conclusion for the second order trend surface, what we can say is that the model doesn't improve that much. Even we have the same problems that is related with this outlier, right? The histogram, it is improvement a little bit, but it's not that much in order to consider a big difference between the first order trend surface and the second order trend surface. And then at the end, I'm going to say that there is no improvement changing from the first order to the second order. We have the same problem associated with this outlier over here. And let me show you how we can identify this outlier on the map. Then we can go to the attribute table, open attribute table. We know the outlier is associated with the highest value for the residual. Then just select this one over here. And then you are going to see the problem is now because the data set is yellow. Then we can change the color. Symbology for a different color. That could be this kind of green. Apply. Okay. And now you can see that the yellow one, maybe the green is not the best color. We can select a blue one, for example. Apply and OK. As you can see, the yellow one is the one selected at the attribute table. Then this value over here is the outlier, distributional and also spatially. Then as I want to use the ordinary least square for the universal Kriging, I'm not going to change my regression model. That one is going to be part of the third lesson where we are going to work with regression Kriging, and we are going to see in that lesson if we change the regression model, we have maybe an improvement on the data set. I don't know because I didn't did yet, but we are going to see that one at the third lesson. But in this lesson, as I want to use the ordinary least squares for the regression model, what I'm going to do is remove this data point from the original data. Because if I leave this data set over here, the regression model is no good. But the rest of the points, the rest of the data is good. Then for just one data point, you know, we cannot use the rest of the data, right? Then what I'm going to do is remove this point from the original data and work with this data set without this point. And I know a lot of people, they are not going to be happy if I remove this point without any justification, but my justification is that the model doesn't work, and that's it, you know. And could be a lot of problems related with this measurement over here, right? We don't know, for example, if the person who took this measurement took a wrong number, or maybe the instrumentation, it doesn't work well that day, or maybe the piezometer is screened in a different hydrogeological unit. Could be a lot of different things, right? There are just two options that are going to avoid to remove that point from the data set. The first point, for example, if there is a person that is a specialist in that area and he knows everything about this area and he knows everything about this well, and he is pretty sure that the well it's perfect, it's well screened, it is the same hydrogeological unit, and he was measured that groundwater elevation for many years, and he know exactly that the value for the groundwater elevation is correct, okay? Then in that case, we cannot remove that data point from the data set, right? Because we know it's that point it's perfect and we cannot remove it, right? And another reason, for example, is that we repeat the study and we go to the site again and we measure again and we get the approximately the same value, right? And if we make several measurements in a different moments, in a different days, and we are still having the same value, and also we know that the well is well screened, then we cannot remove that data from the data set because we know it's well. Then we have to adapt the model to the field conditions, right, to the measurements. Then maybe for this case, we cannot use universal Kriging because maybe we cannot remove that point from the data set. But it's not our case, right? We don't know anything about that data set. And the point is that the model doesn't work well because of that point. Then the solution at this point is to remove that point from the data set. And for the regression Kriging, we can see if we can use any other regression model that can help us to keep that point on the data set. Okay? But I'm not sure 100%. Maybe we cannot use that data point even for a regression Kriging. We are going to see that one at the third lesson. Then now I'm going to load a new vector file that is going to be the same data set but without this point. And I already calculated the first and second order trend surface in that vector file, and we can use that one directly. Because I don't want to repeat all the process, you know how to do it. It's the same as we did for this one, but without this data set. Then I'm going to add that layer. Then it's going to be a vector layer. And it's going to be this shape file. And it's going to be this one. Open and add and close. And let me see. Is the green color. Then if we took this one out, you are going to see that for the new data set, let me change the color, properties. I'm going to put a blue color, for example, apply. And as you can see for this one, you have that data set but for the new shapefile, we don't have that doc with data set over here, has been removed, okay? But for the attribute table, we have again all the information, okay? From this one to this one, all these 4 columns is considering that data set. But for this one to this one is without that point of data, okay? Also, as you can see over here at the ID, the point number 6 doesn't exist. It's that point, okay? The number 6 is the outlier. Then now we are going to do again the histogram with the box plot, the scatter plot, and also the residuals with the bubble to see how it looks like, okay? But with the new values, that is going to be these ones: residuals first order, remove outlier; predicted first order, remove outlier; residual second order, remove outlier; and predicted second order, remove outlier. Then first I'm going to use the script number 13. This one over here. I'm going to select this one, that is the new data set. The parameter is going to be the residuals for the first order, remove outlier. Then I'm going to fill all these ones, but I'm going to pass the video faster. I already added all the data. Now I'm ready to run the script. Double click to open, and let's go to make this screen bigger. Now, as you can see, we don't have longer outlier, a distributional outlier. Also, the box plot is situated at the middle of the graph, and the mean value and median value, they are pretty close each other. And also the data looks pretty symmetric and normally distributed. If we compare this first order trend surface after removing the outlier with the original one, we are going to see that there is a big difference. This one is the original one, and this one is with the remove outlier. Now let's go to do the scatter plot for this one. Then go here, and it's script number 19. Double click to open. And I'm going to add the information, but I'm going to pass the video faster. I write everything. Now it is ready to run the script. Double click to open. Let's go to make this one bigger. And we have here the residual values, and here we have the fitted values. And now you can see that the distribution of the data, it's better than before. Now we can compare with the original data for the first order, and it was this one, and now what we have is this one. Scatter plot, residuals versus fitted, first order, remove the outlier, okay? And now we can do the bubble map. Then we can go here, and the bubble map is number 53. Then double click to open. And in this case, it's going to be this one. X is going to be the X coordinate, Y is going to be the Y coordinate, and Z in this case is going to be the residuals for the first order, remove outlier. Now I'm going to fill all these ones. I already wrote everything that is ready to be run. Double click to open, and let's go to make this one bigger. And now the improvement, it's pretty significant. As you can see now, most of the circles, they are equal, indicating approximately that we have the same error. Also, the distribution of the positive and negative values for the residual are pretty random. Now we can compare this one with this one. That is the original data. As you can see, we have this one very big compared with the rest of the residuals. But in this case, they are pretty equal, most of them, okay? And that's pretty good. Then the conclusion for this first order trend surface after removing the outlier. We have normal distribution. There is no relation between the fitted values and the residual values, as you can see in this graph, and also as you can see in this graph. And we can assume here that we have the constant mean And also for the third assumption, we can say that we have also a constant variance. Now let's go to do the same, but for the second order after remove the outlier. Then go here and we are going to start with the histogram. Then over here, we are going to add here the second order. And I'm going to change that one, but I'm going to pass the video faster. This one is ready. Run. Double click to open. And let's go to make the screen bigger. And as you can see, again, the box, it's approximately at the middle. In this case, the mean and the median, they are pretty together. I'm going to say that they are at the same line even. And also we remove the outlier. Then if we compare this one with this one, we can see an improvement. And the data also, again, it's normally distributed. Now we are going to do the scatter plot. Then go here, move this one to over here, and the scatter plot. I'm going to change these values here for predicted and here for the residual for the second order. And here I'm going to put second. And run. Double click to open. And let's go to make this screen bigger. And again, that one is pretty good. It shows that the mean is constant, and also we are not going to have problems with the variance. And there is no relation between the residuals and the fitted values. And the last one is going to be the bubble for the residuals, this one. Then here we want to put this one, and here we want to change that one for the second. And let's go to make a space here. And we can run this one also. And double click to open, and let's go to make this screen bigger. And again, the residuals, we can see that there is no any pattern on the graph. There is no any trend, and also the bubbles are more or less the same. We don't have a big bubble. And if we compare with the other one, that it was this one, no, this one, and this one. That's the original data for the second order trend surface, and this one is when we remove the spatial outlier over here, and the improvement is significant. What we can say here is that the second order for me at the moment looks better than the first order, but we can do cross validation to see what model has the best root mean square error. Then according to that one, we can decide if we can take the first or the second order trend surface, okay? That is going to be our criteria to decide at the end what model we are going to take for the universal Kriging. To finalize this section related with the bivariate analysis, I would like to show you how you can do a bubble map here in QGIS. At the first lesson, we did a graduated map, but in this case, I would like to do a bubble map to show you the trend on the groundwater elevation. Then what I'm going to do is duplicate this layer, then just select the layer and duplicate the layer. And I'm going to change the name here. Rename the layer, and it's going to be welcome. And I'm going to put here bubble. Then we can go here to properties. Here we are going to select this one over here. Then we are going to press this option over here. And then we are going to go to Assistant. Then here we are going to select the parameter that is going to be the groundwater. And here we are going to refresh to have the maximum and the minimum. And here we are going to apply transformed curve. Then we are going to look for something that we like, something like that, you know, showing the biggest, too much bigger than this one, right? And then OK. And then go here and go to Advanced, Symbol Levels, not this one, this one, and here we can select the legend we want, and I want this legend. OK, apply, and OK. And maybe open, we can edit a little bit this one with some transparency here. Apply, and OK. Even we can change the color. I don't like that color. Properties. Let me select something like that. Apply, and a little bit more transparent. Apply, and OK. I like it here. As you can see, we have the bigger circles are indicating that the groundwater is close to the surface, okay? As the circles are getting smaller, it is indicating that the water is more deeper, okay? And as you go to the attribute table, here for the groundwater elevation, remember that this groundwater elevation is above of sea level, right? Then here we have the groundwater elevation about 1 kilometer from the sea level, and for the minimum value we have around 300 meters from the sea level, right? Then here the groundwater is closer to the surface, and for the small circles are the groundwater more deeper, okay? Even I cannot see well on the map. Let me change for a yellow color. And apply some transparency. Apply. Okay. And that's the way also we can see on the map the trend, that there is a trend on the data, right? Because it's pretty clear that the groundwater is moving from here to this direction, okay? Well, that's it for the bivariate analysis. Now let's move on to the structural analysis. And I'm going to go faster because the structural analysis is going to be pretty similar as we did for the ordinary Kriging. But the only thing is changing is the script, that in this case we are going to use a script that is going to be related for the first or also for the second order trend surface.